The organic group is going to be added to the fatty acid, giving us the new ester, the methyl ester, or the fatty acid methyl ester. So here's the methodology of our procedure. Our methodology involved multiple steps. First, we had to cultivate the algae, extract the algae oil, purify the oil, transesterification reaction converting the oil to the biodiesel, and finally washing and purifying, separating, washing and purifying the biodiesel. First, so we acquired the algae from Aqaba on May 5th, 2018. This was around a year ago. After we got the algae, we had to transfer it to a cultivation vessel, which is the aquarium, also known as the photobioreactor. Photobioreactor is a reactor that allows for photosynthetic organisms to grow. The culture medium was water, which has certain parameters that we had to monitor. These parameters are the water salinity, the CO2 oxygen supply, the temperature, and the pH. So the temperature for our reaction needed to be from 20 to 24, meaning we didn't need additional heating since that's room temperature. The pH had to be between 7 to 9, and when we checked it, it was usually 8, which was fine within our parameters. Sunlight, we didn't need additional light source since we had our aquarium near a window, and it was during the summer, so there was continuous sunlight supply during the morning, which was fine for the photosynthesis. Okay, so the water salinity is the salt that we had to add to the water. So to check, to know how much salt to add, we had to check the aquarium dimensions, and from that, find the water volume, calculate the water volume, which was 86.4 liters. From that, we can know that for 36 parts per thousand salinity, 36 grams are added per liter. For that, we added 3 kilograms of salt to have the perfect salinity for cultivation. Here you can see, as I said, we need oxygen supply. We have an air pump inside the cultivation vessel so that it can cause continuous aeration and oxygen supply to the organisms. And to test our pH, we use the pH strip. We place it inside the water, and then you compare the result with known values, and our value is between 8 and 9 pH.
Jeanine, was it CO2 or O2?
No, CO2, we use the CO2 cylinder. Oh, can you go back 2 slides? Here you can see, it's not really showing. There's a CO2 cylinder. It supplies them with CO2 for photosynthesis. And the pump, because when they photosynthesize, they release oxygen, and the pump allows the oxygen to mix with the organism.
So a stock-slit extractor device was used to extract the algae, the oil from our algae samples, using N-hexene solvent. As you can see here in the figure, the stock-slit device divides into 3 main sections. The first one is the distillation flask, where our N-hexane is filled with. The other one is the extractor chamber, and the other one is the condenser. And here is our algae sample. It's filled in the cylinder thimble, housing the extractor chamber. Okay. The working principle for the stock-slit extraction is very simple and easy. First of all, the system needs heating source. The N-hexane is heated until boiling. When it starts to evaporate, the vapor travels through the arm, reaching the reflex condenser, and then the vapor cools and condense, and then it will drip back down into our sample. The warm N-hexane will extract the oil from the algae, and as the extractant feels almost full, it will empty through the siphon back to the distillation flask. It's a continuous procedure. In our case, it took for 4 days, 6 hours each day. And of course, the extraction conducted under fume hood or in fume hood to protect ourselves from hazardous fume or hazardous vapors. So the next step after the extraction has been completed, now we need to separate N-hexane from the algae oil. To do so, we used a rotary evaporator. Rotary evaporator is a device that separates solvents from our samples using evaporation. As you can see here in the figure, here is the rotary flask that contains our mixture, the NHCN with the algae. And the water bath supplies heat to the mixture. And the mixture is heated until it reaches the boiling point less than the boiling point, but it heats until the N-hexane starts to evaporate. As the hexane evaporates, it will travel to the condenser. It again will condense and will be collected in our collection flask. The rotary evaporator's parameters. The temperature for the water bath was 40 Celsius. It's less than the boiling point of the N-hexane, but we were working in a vacuumized system. The rotation was 45 revolutions per minute, and the duration for our procedure was 15 minutes. The pressure was 370 millibar. When we reduce the pressure, when we decrease the pressure, we reduce the boiling point for the solvents, that it can evaporate at less temperature than the atmospheric pressure. Okay, for further purifications, we used syringe filters to remove any impurities from the biodiesel, from the oil, sorry. And also this procedure, we can use it later on for the biodiesel.
Okay. So the acidification reaction which we conducted, it involved, again, it's a reaction that converts the oil to the biodiesel. It involved multiple oils. We wanted to compare different biodiesel products. So we used soybean oil, corn oil, cooked corn oil, and the algae oil, of course. We used a base catalyst. As I said, base catalyst gives the most efficient results, and since our oil did not have a high FFA content, we did not require the use of an acidic catalyst. The alcohol used is methanol. It could be either methanol or ethanol, but we felt like the best results were obtained using the methanol alcohol. Together, when we add these together, we have the potassium hydroxide solution, which is also known as the catalyst solution, which I'll show you in the next slide how we use it. Okay, so first we had to heat the oil to a certain temperature. The temperature we chose was 55 Celsius, since methanol evaporates at temperatures over 60, and we did not want to lose the methanol when we added it. After we heated the oil, we removed it from the hot plate, and then we added the catalyst solution to the oil and placed it on a magnetic stir plate. There's no heat in this part of the procedure. We just covered it with aluminum foil to prevent loss of the alcohol. The stirring time was 30 minutes. We kept it on the magnetic stir plate for 30 minutes. The total reaction took 15 minutes, since the catalyst preparation time is around 10 minutes. And after that, we transfer the biodiesel with the glycerol mixture into a separating funnel and let it settle for 24 hours. So, as I mentioned, we use different oil types, but not only that, we use different oil volumes. Depending on the oil volume used, we would choose the catalyst solution volume calculated through an equation. The reason we use different oil volumes is since we wanted to lower the original volume, we tried to minimize the reaction, since our algae oil was around only 4 milliliters. The catalyst solution volume, which is again the methanol with the catalyst, had to be kept in mind. We had to keep in mind the 6:1 molar ratio which we spoke about before, which is why it's actually higher than the actual alcohol for a complete reaction. Here's how we separate the biodiesel. As I said, we let it settle for 24 hours. Glycerol is the new alcohol, and biodiesel is the new ester. Glycerol is higher in density than biodiesel, which is why it settled to the bottom. We allowed it to settle for 24 hours, and then we simply removed it with a separating funnel. In the case of the algae oil, we chose to use a burette since it has a really small diameter, and the algae biodiesel is really small in volume, so we didn't want to lose the biodiesel sample.
Okay, so biodiesel should be washed, glycerol, or any contaminants in the biodiesel. The volume of the water should equal to the volume of the biodiesel, and our separating funnel should be set for 3 minutes. The test can be repeated twice for optimal results. Okay, so biodiesel can degrade due to oxidization, contact with water, and microbial activity. And also, it has the tendency to freeze at higher temperatures than the biodiesel, than the petroleum fuel. So in our case, we stored the sample using sealed aluminum foil, and it was stored in a dry, dark place within the fume hood. The results for our extraction and transesterification. The volume for the extracted algae was 4 milliliter, as you can see in this image. And the volume for and the 15 milliliters of N-hexane was lost during the procedure of sock slit extraction. 0.5 milliliters of algae biodiesel was our final product, as you can see in this picture. We calculated the percentage yield for the different sources of biodiesel, oil. And here's the equations we used. The VF represents the final fuel volume. The V initial represents the initial oil volume. And here's the table shows the results for the percentage yield of each oil.
So from the percentage yield results, which she just spoke about, we have different higher yields for different oils. We felt like the highest yield we got was from the soybean oil, which gave us a nearly perfect result, around 95% yield. And from these results, we were able to find a linear relationship between the oil volume and the percentage yield. Therefore, the higher the oil volume used during transesterification, the higher the percentage yield in material. There are international standards organizations that evaluates different standards for different materials and products and services. Here you can see results of our test. So the passing result would be a clear phase, whereas the failing result sometimes gave us oil droplet. The biodiesel result we mentioned within the presentation to check the yield percentage. We chose only the tests that passed the results for the optimal results of our experiment. So for conclusion, we wanted to evaluate our work. Oh, before the conclusion, sorry. So there is another test we conducted. It was called the gas chromatography test. We conducted the test, however, we weren't able to add our results since due to weather conditions, we weren't able to process our results last week, so we weren't able to include them. And they need more processing from us, so hopefully we'll add them into our thesis later on. Thank you, Dr. for helping us with this. To evaluate our work, we thought that our successful aspects were the extraction of the oil, the purification of the oil, the transesterification reaction of the different oils, separating the biodiesel from the glycerol, purifying the biodiesel, and finally storing the biodiesel. However, we felt like we fell short in cultivating the algae since after a few weeks it began to shrink and change color. It became to discolor, which is why our percentage yield was really low compared to all the other ones since we had a really small volume of oil to work with. For future suggestions to prevent such problems or drawbacks, we believe that a better understanding of the algae habitat, which is Aqaba's Red Sea, to mimic the environment of the algae, you have to understand it way better, know the nutrients and the exact salinity, since the salinity changes from parts of the sea, from parts to parts. And also, drying of the algae before extracting the oil would be preferable, which we weren't able to do since our algae was a mixture of sludge and dead algae and dirt. We couldn't separate it and purify it prior to extraction. Here are the references we used during our presentation. I hope everyone enjoyed. I want to thank again everyone for attending, from our teachers, our friends, our families, and everyone.
Jeanine, any questions please from the audience?
No?
questions?
No.
Can you please leave the room?